Mercury is the planet closest to the Sun, lying just about 36 million miles away. Despite its unique position in our solar system, Mercury was long thought of as a barren, unremarkable world. But recent discoveries show that Mercury has some remarkable features that make it much more interesting than it first appeared. Surprisingly, Mercury has water ice at its poles, a finding that startled scientists given the planet's intense heat near the Sun. Additionally, Mercury's surface is dotted with rare impact craters and unusual landforms that aren't found on other planets. These features add to Mercury's mystery and suggest that it's experienced a fascinating geological history. Though Mercury is small, it has a magnetosphere that's a magnetic field that can deflect some of the Sun's charged particles. It even has a very thin atmosphere, or exosphere, which is surprising for a planet so close to the Sun. This magnetosphere and thin atmosphere, while weak, provide clues to the planet's inner structure and past conditions. Mercury is a small, rocky planet with a radius of about 1,516 miles, making it just slightly larger than the Earth's moon. It's the closest planet to the Sun, orbiting at an average distance of 36 million miles. A year on Mercury, or the time it takes to complete one orbit around the Sun, lasts only 88 Earth days because of how close Mercury is to the Sun. With almost no atmosphere to trap heat, Mercury's temperatures vary drastically. During the day, surface temperatures soar to around 800 degrees Fahrenheit, while at night, without the Sun's warmth, they plummet to a chilly -290 degrees Fahrenheit. One day on Mercury, meaning the time it takes for the planet to rotate once on its axis, is extremely long. While Earth completes one rotation in 24 hours, Mercury takes about 59 Earth days to finish a single rotation. Mercury's rotation is influenced by something known as a spin-orbit resonance. For every 3 times Mercury rotates on its axis, it completes 2 orbits around the Sun, which creates a unique 3-to-2 relationship. This resonance means that during its orbit, Mercury turns slowly enough that its day is almost 2/3 the length of its year. Scientists used to think that the Sun's gravitational pull had tidally locked Mercury, meaning one side would always face the Sun. However, Mercury's actual spin-orbit pattern suggests a different story. One theory is that Mercury might have been in a different spin state long ago. Some scientists believe a massive collision could have shifted its rotation to the current 3-to-2 pattern. Another study, led by Benoit Noël and his team, suggested that Mercury could have been in its current resonance state since its formation. This ongoing research helps explain why Mercury's rotation and orbit are unlike those of other planets. Mercury's orbit is quite different from that of other planets. Instead of being a perfect circle, its orbit is more elongated or eccentric, stretching from about 29 million miles to 43 million miles away from the Sun. This means that at certain times, Mercury is much closer to the Sun than at others. This uneven orbit not only causes big temperature swings, but also makes Mercury's speed change as it moves around the Sun. When it's closest, or at perihelion, Mercury zips along faster. Then, at its farthest point, or aphelion, it slows down. This unusual orbit impacts everything from Mercury's surface temperatures to how its weak magnetic field interacts with solar winds. One of the most surprising discoveries around Mercury is a dust ring that lies along its orbital path. Dust rings are created when particles from meteoroids get trapped in a planet's orbit. Although Mercury's dust ring is faint, it's still significant because it adds to our understanding of the solar system's debris environment. Meteoroid impacts on Mercury's surface may throw dust into space, which gets pulled into orbit by the Sun's gravity. This dust ring could also help us learn about other inner planets and the origins of cosmic dust in our solar system. Mercury's magnetosphere is weak, but unique for a planet so small and close to the Sun. This magnetic field, while not as powerful as Earth's, still manages to push back some of the sun's charged particles, creating a protective layer around the planet. However, this magnetic shield isn't strong enough to keep all solar wind out. Observation by NASA's Messenger spacecraft revealed magnetic tornadoes, twisting funnels of magnetic energy that allow solar wind particles to leak through Mercury's magnetosphere. These magnetic tornadoes, and the leaky nature of Mercury's magnetosphere, contribute to unusual space weather conditions on the planet's surface, shaping its environment in ways we're still trying to fully understand. Mercury has an exceptionally large core for a planet its size, with metallic elements like iron taking up about 1/3 of the planet's total mass. This makes Mercury one of the most metal-rich planets in the solar system. Its core is not only massive, but may also still be partially liquid, as scientists discovered from the way Mercury's magnetic field changes. This liquid core might be responsible for generating Mercury's weak magnetosphere, similar to how Earth's core generates its magnetic field. The formation of Mercury, with its high metal content and dense core, raises intriguing questions. One theory is that Mercury formed close to the Sun in a metal-rich part of the protoplanetary disk, the cloud of gas and dust that gave birth to the planets. In this environment, heavier metals may have clumped together to create a dense, metal-heavy planet like Mercury. Another theory suggests that Mercury may have started out much larger, but lost much of its rocky outer layers. Some scientists propose that huge impacts from other large space objects or the gravitational influence of Earth and Venus could have stripped away Mercury's outer material, leaving behind its metal-rich core. If true, this would mean that the Mercury we see today is a survivor of intense planet-shaping events in the early solar system. Studying Mercury isn't easy, mainly because of how close it is to the Sun. From Earth, we can only see Mercury for short periods during sunrise or sunset, when the Sun's glare isn't overwhelming. Even then, Mercury's small size and distance from Earth make it hard to observe in detail. This limited viewing window means astronomers need to use specialized telescopes and careful timing to gather information. Sending spacecraft to Mercury is a complicated task due to the Sun's powerful gravitational pull. Spacecraft traveling toward Mercury accelerate quickly, and slowing down enough to be captured by Mercury's gravity requires a lot of fuel and careful planning. Additionally, the intense heat from the Sun make it challenging to design spacecraft that can survive the extreme temperatures near Mercury. The first mission to explore Mercury was NASA's Mariner 10, which launched in 1973. Mariner 10 was a pioneer for several reasons, using Venus's gravity to slingshot toward Mercury, a technique called gravity assist. This maneuver allowed Mariner 10 to make 3 flybys of Mercury between 1974 and 1975, capturing detailed images of Mercury's surface for the first time. Through these flybys, Mariner 10 uncovered Mercury's magnetic field, a surprising discovery given the planet's small size and lack of a thick atmosphere. It also found clues about Mercury's metallic core, which makes up a large part of the planet. Mariner 10's images revealed a surface covered with impact craters and smooth plains, giving us our first real look at Mercury's rugged landscape. NASA's Messenger, Mercury Surface Space Environment, Geochemistry, and Ranging mission was the first spacecraft to orbit Mercury, launching in 2004 and remaining active until 2015. Messenger orbited Mercury over 4,000 times, gathering extensive data on the planet's composition, geology, and magnetic field. One of its primary goals was to create a full map of Mercury's surface, which it successfully completed. Messenger also found evidence of volcanic activity and studied Mercury's weak magnetic field in detail, revealing that it's slightly offset from the planet's center. Messenger's instruments detected water ice at Mercury's poles, where deep craters shield the ice from the sun's heat, offering a surprising clue that even a planet so close to the sun could host frozen water. Messenger made several groundbreaking discoveries. It revealed that Mercury's surface has a unique chemical composition, different from that of other rocky planets, hinting at its distinct formation history. It also found signs of ancient volcanic activity, which helped shape parts of the planet's surface. Additionally, Messenger's observations confirmed that Mercury has water ice deposit at its poles and revealed a mysterious shift in its magnetic field, slightly off-center from the planet's core. Mercury's surface is a mixture of rugged craters, relatively smooth plains, long ridges, and shallow troughs. The craters vary in size and are scattered across the planet, with smoother plains filling some areas. These plains are likely the result of ancient volcanic activity that smoothed over parts of the surface. Additionally, Mercury's terrain reflects its long history of meteor impacts, volcanic events, and the effects of cooling and shrinking over time. Impact craters are one of Mercury's most prominent features, and they come in two main types: simple craters and complex craters. Simple craters are small, bowl-shaped depressions, while complex craters are large with central peaks or ring-like structures formed by the rebound effect of an impact. The largest crater on Mercury is the Caloris Basin, stretching over 960 miles across. Other notable craters include Rembrandt, which shows signs of planetary tectonics, and several smaller craters with unique features. Mercury's craters preserve a record of impacts going back billions of years, offering clues about the planet's formation and history. Mercury has a few rare types of craters that stand out. Elliptical craters are formed when objects strike the surface at a shallow angle, creating an elongated shape. Polygonal craters have edges that form straight lines or corners, thought to result from Mercury's crustal stress patterns. Ghost craters are old craters that have been filled in by lava flows, leaving faint outlines, while ray craters have bright streaks radiating from them, formed by ejected material from recent impacts. These unique crater types reveal the variety of processes that have shaped Mercury's surface. Unlike Earth, Mercury has very few high mountains, or large mountain ranges. The planet's surface has some ridges and escarpments, steep slopes found as Mercury's interior cooled and contracted over time. This contraction caused the crust to wrinkle and form these ridges, some of which stretch for hundreds of miles. These features are clues to Mercury's shrinking size, a process that has shaped much of its surface. One of Mercury's most unusual surface features is its hollows. These are shallow, irregular depressions scattered across the surface, with bright edges that make them stand out. Scientists believe these hollows may have formed as Mercury lost volatile elements, substances that vaporize easily. When these elements escaped into space, they left behind hollowed-out areas in the crust, a process that likely continues even today. Mercury's smooth plains are relatively flat regions, likely formed by volcanic activity. Unlike the rugged, cratered terrain that covers much of Mercury, these plains have fewer impact craters, suggesting they're younger than other parts of the surface. Volcanic eruptions may have poured lava across large areas, filling in old craters and creating smoother land. These plains add to the evidence that volcanic activity played a significant role in shaping Mercury's surface, especially in its early history. The European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, joined forces to launch Bepi Colombo, a mission to explore Mercury more deeply than ever before. Launched in 2018, Bepi Colombo is named after Giuseppe Bepi Colombo, an Italian scientist who studied Mercury's orbital path and helped with Mariner 10's successful mission. This mission represents an exciting opportunity to uncover many of Mercury's secrets that remain unknown even after previous missions. Bepi Colombo's main objectives focus on studying Mercury's magnetic field, mysterious surface features, and even the water ice discovered at the planet's poles. Unlike previous missions, Bepi Colombo is equipped with two orbiters that will work together to provide detailed data from different perspectives. One orbiter, the Mercury Planetary Orbiter, will map the surface, analyze surface composition, and search for evidence of volcanic and tectonic activity. The other, the Mercury Magnetosphere Orbiter, will focus on studying the magnetic field, magnetic tornadoes, and how the solar wind interacts with Mercury's magnetosphere. Together, they'll study Mercury's strange, hollows, bright, shallow depressions that appear unique to the planet, and investigate how they were formed. Scientists are also interested in how Mercury's surface changes over time, especially due to its intense temperature fluctuations. Bepi Colombo will observe these temperature shifts and look for surface changes, which could give clues about Mercury's composition and how it has evolved over billions of years. The mission will also study water ice deposits at Mercury's poles, protected from sunlight in shadowed craters, which is especially surprising for a planet so close to the Sun. After its launch in 2018, Bepi Colombo began a long journey toward Mercury, using gravity assists from Earth and Mercury itself to help slow down and steer it closer to its destination. This complex path will finally bring Bepi Colombo into Mercury's orbit by 2025. Once there, it will begin its observations and data collection, expected to last several years, giving scientists an in-depth look at Mercury that could reveal new findings about the planet and its place in the solar system. The Bepi Colombo mission is essential to helping scientists understand not just Mercury, but also the early history of the solar system. Mercury's extreme environment, its unique magnetic field, and its high metal content make it unlike any other planet. Bepi Colombo's findings could provide insight into how Mercury formed and how it survived close to the Sun's harsh radiation, helping us understand the evolution of other rocky planets, including Earth. The mission will also help scientists learn more about planetary magnetism. Mercury's magnetic field and magnetosphere, though weak and lopsided, are incredibly interesting. Bepi Colombo could explain why Mercury's field is so different from the Earth's and how it behaves under intense solar wind. With its high-tech equipment, the Bepi Colombo mission is expected to answer many questions about Mercury's surface, magnetic field, and history, and perhaps raise new ones. The information it gathers will add a crucial piece to the puzzle of how planets close to the Sun develop, survive, and change, bringing us closer to understanding our own planet's origins and the solar system as a whole.